Welcome to this short series of talks where I'm going to give an introduction to the rich interplay between non-Archimedean uniformization and tropicalization, with particular focus on a non-Archimedean version of Teichmüller space and the moduli space of smooth curves. All of what I'm going to say can also be found in this preprint that, with this archive number. And if you are interested, feel free to check it out or come to the conversation session during the conference at Imperial College where you can just talk to me about this as well. Okay, just let's get started with some motivation. So there are as many approaches to tropical geometry as there are tropical geometers. And in many ways, that's a great thing. My favorite one, however, is the strange but somewhat surprising analogy between the geometry of compact Riemann surfaces and of metric graphs. So, for example, there is a rich theory of divisors on compact Riemann surfaces that we're all aware of. I mean, it goes back to Riemann. And there's similarly also a rich theory of divisors in linear systems on metric graphs. And this is not just a rich theory that goes in analogy, but we can also use insights from this theory on metric graphs to prove strong and even stronger than classically known results on linear series on compact Riemann surfaces. So when we study this, we have to be a bit careful. There is sort of a few things that make our life easier. For example, in this case of compact Riemann surfaces, it's, at least for our purposes, easier to think of them as smooth projective curves, because then, I mean, over the complex numbers, because then we have all the methods of algebraic geometry at our hand, which allow us, for example, to study deformations of such surfaces. You can do it in a complex geometric world as well, but there's a lot that is already developed in the algebraic world. It's a complex geometric world. You have to look for a while till you will actually find the right techniques. Okay, so why do we want to study deformations? Well, in a way, studying deformations of geometric objects reveals hidden geometric properties. And so it comes as no surprise that we also would want to study deformations of metric graphs. So, okay, how can this metric graph here deform? Well, we could, for example, just shrink the left loop and make it smaller and smaller until it just vanishes because it has length 0. And that really should be an allowed deformation. But this deformation comes with a problem. So if we think about the first important invariant of a compact Riemann surface, or Riemann surface in general, it's its genus. So easiest here is just to say it's 1/2 the first Betti number. So it's a topological genus. First Betti number, there is the dimension of the first homology group. And intuitively, it just is like the number of, so if you imagine a compact Riemann surfaces as like a collection of donuts that have been stuck together and the surface thereof, then the genus is the number of holes of this surface of a baking experiment gone wrong. And the most important thing to know about genera in deformations is that they stay constant in flat deformation, flat and proper deformations. So we would want to have something similar to go on in the case of metric graphs. But our first attempt would, of course, be, yeah, we want the number of holes of this metric graph. So it's 2 here, it's 2 here. But suddenly at that point where the edge length goes to 0, it suddenly does, we just suddenly don't have the sort of number 2, but rather number 1. And the trick is to somehow artificially remember that there used to be, that there is sort of an infinitesimally small loop at this vertex by decorating it with the number 1. So really, in this analogy, the good thing to think about is not the metric graph, but rather the tropical curve, which is, well, a metric graph gamma, together with a function from the metric graph to the non-negative integers with finite support. Okay, and then we can define a genus function of the metric graph as follows. We take the first Betti number, that's now the number of poles here, I mean in this case of the underlying metric graph, plus, to keep the genus constant in families, the sum over all points in the metric graph, which is a priori infinite, but actually finite, over these vertex weights, or these weights at some points, because this has a finite support. So this is really a finite sum. And for example, in the example up here, we end up seeing that here it's genus 2, here it's genus Betti number 1, plus this 1 over here, so it's still genus 2. Okay. That's just the first sort of big observation, or first observation to think about this analogy further. Now, really a good question is, well, there are interactions, so how can you formalize the sort of the close connection between those two objects? And the idea to do so is to use smooth projective curves over some non-Archimedean field. So for example, over the field of Puiseux series. So you can now think of the underlying Berkovich space of this thing, which ends up looking something like this. So this witch's broom picture that is probably very familiar to all of the participants of the conference. So we have infinitely many of these edges coming off, but you have sort of a combinatorially defined central part of this in this picture that looks exactly like the metric graph, and this is the so-called skeleton. So one way to connect it is you have this picture of the Berkovich analytic space, and then the metric graph is a skeleton of the Berkovich analytic space above. And there's also a way to connect this to compact Riemann surfaces, because, well, this Berkovich analytic space of a smooth projective curve over, say, the Puiseux series field can really be thought of as the generic fiber of a family of compact Riemann surfaces close to a boundary point, say. Okay, so there is this very intricate connection between compact Riemann surfaces and metric graphs going via Berkovich analytic spaces. And sort of a common theme now is to also generalize these correspondences on the level of moduli spaces. That has been done, and we'll look at how it is done, at least in a superficial kind of way. So you have on the one side the moduli space of smooth algebraic curves of genus G, which is a smooth Dirichlet-Mumford stack separated for finite type. And you can compactify if you want, but we'll not worry about that at this point. And on the tropical side, you also have a moduli space, the moduli space of stable tropical curve of genus G. We'll see an example of this in a second, but I mean, essentially it's just isomorphism classes of tropical curves of genus G with some stability condition, which just avoids some bad outgrowths of the graph. And the connection between those two is, again, we can go to the Berkovich analytic space associated to the moduli space. which is, of course, a non-Archimedean analytic stack. Also has very good properties. And then there is another connection of this stack with the tropical moduli space. And in fact, the tropical moduli space is now again a skeleton of the Berkovich analytic space up here. And this is has been worked out only 5 years ago. I mean, more than 5 years ago, but it has been published 5 years ago in a work by Abramovich, Caporaso, and Payne, and it has been published in 2015. It just explains to us that the tropical moduli space is a skeleton of the non-Archimedean analytic analytification of the algebraic moduli space. And just to give you a bit of a hint of what this tropical moduli space actually is, we'll just work on an example of it so we can get our hands on it if we want. And the easiest example is G equals 2. So let's study it. And the way to study these tropical moduli spaces is to realize that such a metric graph has an underlying topological model. I mean, this one has one vertex here, edge, two edges here. This one only has one vertex, one edge, only two edges, and this particular vertex weight. So these are different combinatorial types, and you have to check how these combinatorial types deform into each other when you let edge lengths go to 0. And that, in fact, gives us a form of poset of these combinatorial types. So let's draw this first. So the types of stable vertex-weighted graphs of genus 2. So what are the possibilities? One is the one that we already saw. That's this one. And you can also get a theta graph that looks like this. And those two are not isomorphic. Okay, as we saw, we can let one of those loops go to 0. That gives us another type, and we can let the other one go to 0, which gives us this type. Similarly, we could have also taken the middle one, the middle edge, so this bridge, and let this one go to 0. And we end up getting this combinatorial type, which we also find if we let this edge, for example, here go to 0, or this one, that up to isomorphism does not cause any problems. So we end up getting there. Then at this point, we can let one of the loops go to 0, or we can let this bridge edge or former bridge edge go to 0. So we end up getting a combinatorial type like this. And finally, we can either let the former bridge edge go to 0, or let this loop go to 0 and combine the two vertices to 1 and end up getting this type of combinatorial type. Okay, so these are all the types of stable graphs of genus 2. And now the question is, before we sort of use this idea or this structural idea to study the tropical moduli space, I want to sort of point out, I just said poset, and well, I use quotation marks because, well, it's not quite a poset. Why is that? Well, I mean, if you think about it carefully, you see that there are automorphisms present. So here we have one that just flips the two sides, the Z-mod 2 automorphism group. Here we again have one that flips the two sides, that's the Z-mod 2 automorphism group. If you look very carefully, you also see you have one that flips the edges and flips these edges, but I'm not even drawing this one. And the most important one is the automorphism group up here, where you have like an S3 worth of automorphism for this theta graph that just permutes all these edges. And even better, well, I've been drawing this picture, but what if we had taken that loop here and had contracted that one to 0? then we get another way of finding an isomorphic graph. So really we should not think of this as one way in a poset, but sort of two ways in a poset, which is of course impossible, but anyway. And same here. And here we have three ways of doing it, because we could have contracted each of these edges. And then we suddenly have an object that just isn't really a poset anymore, because we have these different paths. But if you have a poset, you have inclusions. So, or for example, or I mean, whatever you have in a poset in this order, and then it's not possible to have different paths between two of the same things. So this is not a poset. And solution is, well, not to describe it as a poset, but as something that I did more general, which I'm just loosely calling a stack, which is nothing but a stack over the category of posets, but actually the category of posets is very easy. So it's actually just a category fibered in groupoids over a poset that is automatically a stack, because descent is a no-brainer in this category. If you want to learn a little bit more about what the structure of these moduli spaces looks like, I recommend checking out an earlier paper of mine. It only appeared recently with Cavalieri, Chen, and Weiss in 2020. Okay, going back, now that we have sort of understood what the underlying combinatorial structure of such a moduli space could be, let's try to draw it. And we start by looking at two different maximal types. So like this one will have sort of, will be the cone over a simplex, because you have three edge lengths that can vary. So that's this simplex. But you also have automorphisms being present, namely the one that sends this thing to this thing. So you also have to sort of mod out by these automorphisms. And you only get half of this triangle. The same with the theta graph. You again have three edge lengths. So three parameters that should be r greater or equal to 0 to the power 3. So we take just a cone over the simplex again. But now you have an S3's worth of automorphisms present. So you have to mod out by that as well, the induced permutation. So what you get is just this little bit of the triangle, and with the other things somehow being folded all over. And now we can look at what happens when you let some edges degenerate. For example, if you let one of the loops degenerate, you come to this side. That's this type. Then you let the other loop degenerate, you end up getting this one. And well, at this end, well, you just let the edge degenerate, so you end up getting this one. And well, on the end down here, that's when you let the bridge edge degenerate, you end up getting this combinatorial type. At the same time, when you let either of these edges of the theta graph degenerate, you also get this one. That's why it's here at the intersection. And now we have taken care of all of the types, but you have to imagine that this is really a three-dimensional picture that is namely a cone over these simplices that are here. So then there's the one that's missing is this one, which is sort of the origin of this cone over the picture you have over here. Okay. With that picture in mind, I will end the first video. In the next one, we will talk about uniformization of, of non-Archimedean curves via the methods of Mumford, and how to generalize this to modular spaces. Welcome back now to the story of uniformization of curves and their modular spaces. So let's just review a very classical construction due to Mumford with a sort of new tropical spin, which is probably was known to Mumford, but he wouldn't have used the word tropical yet. So the situation is the following. We have a non-Archimedean field. For simplicity's sake, we can assume it's algebraically closed. It also works when not. And we have a smooth projective curve. And gamma should be a skeleton of the non-Archimedean identification thereof. And by G, we call the fundamental group of the underlying topological space of the Berkovich analytic space. So nothing too fancy. And that turns out to be exactly the underlying, the fundamental group of the skeleton, because, well, the skeleton admits a deformation retract onto it, so that's fine. And therefore, this is the fundamental group of a finite graph. This is so just a free group on B generators, where B is the first Betti number of the graph, and at the same time, the first Betti number of the Berkovich analytic space, being deformation retract of the Berkovich analytic space. Okay, now let's look at the retraction map from the Berkovich analytic space to the skeleton. And we want to construct a uniformization of the Berkovich analytic space here. How will we do that? Well, first, I mean, as I said, we'll consider the retraction to the skeleton. And now we construct a universal cover of this metric graph, which you can always do. I mean, you can also do it when the vertex weight is present, but then the construction will be less interesting, but you can do it. That's the universal cover of gamma. And that is set in a way so that well, gamma tilde, mod out by the operation, by the monotropy operation of the fundamental group, is just gamma itself. And then how will we now construct a uniformization of X? Well, we take the fiber product of this diagram that we call just omega. And that turns out to be topologically just universal cover of the Berkovich analytic space. And well, we have that omega modulo this group G is nothing but X analytified. And in fact, you can do further. You can even check that this thing has sort of, I mean, pre-images of edges and points are affinoid domains, and this thing essentially consists of gluing those affinoid domains according to the universal cover construction over here. So this ends up actually being a Berkovich analytic space, and in fact, it even ends up being a Zariski open subspace of the Berkovich projective line. And moreover, one can show that the operation of the fundamental group is induced from a map to the projective linear transformations of this projective space, and then a restriction to omega. Okay, so that's our very simplistic view of how to construct a analytification of a Berkovich analytic curve. I want to point out that Mumford phrased this very differently, because he really studied sort of the structure of these automorphisms here and so on and so on. And that's in fact much more sophisticated than what we're doing here. But the basic idea of what's going on here will help us later to study uniformizations of modular spaces, which is why we repeat it this way. And before we continue, I want to point out to technique enthusiasts that this is not actually a fiber product, because these objects are not really in the same category. So be careful when you actually want to do this. You can use the techniques that will come into play later to do this in this situation as well. But if not, you just have to sort of use this as a heuristic and then do a different construction for omega as well. Okay, now to the main point of this talk, that's uniformization of modular spaces. And that's really the goal of this whole story. So we start, what is the uniformization of modular space of compact Riemann surfaces? Well, that's Teichmüller space, which was historically there earlier even than the modular space. But anyway, so this Teichmüller space is in the approach that works best for this in this situation, the modular space of pairs, X being a compact Riemann surface of genus G, and phi being an outer isomorphism class from the fundamental group of X to pi g, where pi g is just the fundamental group of our closed genus G surface. So pi g is A1, B1, A2, B2, and so on, up to A1, up to AG, BG, subject to the condition that A1, the commutator product of all of these things, is equal to 1. So that's well known. And on the tropical side, you also have a tropical Teichmüller space, which you can sort of sloppily define as the modular space of pairs, consisting of a stable tropical curve gamma and phi being an outer isomorphism class from the fundamental group of gamma to FB, which is the free group on B generators. And a word of warning, here there is something different happening because this B is really the Betti number of gamma. So the genus of gamma minus all the vertex weights. So something tricky is going on, and we'll get back to this at some point, but this is also the main difficulty in constructing this tropical Teichmüller space. So for just to be on the safe side, this was done by Chen, Milu, and Ribiani for the first time, not in the interpretation with fundamental groups, but they constructed the same space. And this space also contains an even earlier construction, namely when you don't have these vertex weights present. This is nothing but a non-projectivized version of Kaller-Vogtmann outer space. And they used it to study the properties of the group out FG, because, well, it's kind of a K out FG1, but it's not really, but it's close enough. So they do it this way. And this is a construction that predates tropical geometry quite a bit. And there's sort of a very rich geometry behind it. And this is in a way a simplicial compactification, or completion rather, of the space. Okay. Now, the main difficulty is we would like to have a picture similar to the above, where we just analytify Teichmüller space, whatever this means, and get that the tropical Teichmüller space is a skeleton thereof. The central problem of that is, well, that this is not algebraic, so analytifying will be difficult or impossible. So this is a Z-analytic space, and it is not algebraic. So that's the central problem. So really, there's something missing here. And the thing that is missing is what this talk is about. So one proposition of what could be missing here is a space that I like to call sort of TGAN, so a non-Archimedean analytic Teichmüller space. And it has been constructed in this article that I'm talking about. And it is, loosely speaking, the modular space of pairs, where X is a non-Archimedean analytic curve, or an analytification of non-Archimedean, our curve of non-Archimedean field. And phi is now simply a outer isomorphism class from the Berkowitz analytification to the free group in B generators again. And once you have constructed this space and shown that it has reasonable, when it is a reasonable Berkowitz space in a suitable sense, then the central result here will be that this thing, tropical Teichmüller space, is a skeleton of this newly constructed space. For people who know, I want to point out that it is not the same, but very closely related to a different, more representation theoretic construction from Herrlich and Gerritsen, in the 80s. I mean, I'm being a bit vague because there are several papers on it. And they also construct a version of p-adic Teichmüller space, or also sometimes called the Schottky space. And this construction is closely related. It's a bit representation theoretic, so it's not quite the same, but there's a map from this space to that. And the exact thing is, I think, not completely understood at this point. The exact correct is not completely understood at this point, but it's really closely related. Let's say it like that. And of course, the next question is, well, does this have to do anything with the classical Teichmüller space? And the answer is a priori not. There is a little bit of hope that there is a connection, but I really have no idea. Okay. Before we now state the main result of this article, let's quickly try to understand this tropical Teichmüller space a little bit better. And for that, I'm just going to explain a picture that is not mine, but it has been made by Karen Vogtman for outer space, but you can see pretty much all the features. And that's the Non-Archimedean Teichmüller space in genus 2, the tropical Teichmüller space in genus 2. So you again see all the sort of the well-known two-dimensional simplices that we have seen before, but there's now a lot of them. Right here with the theta graph, then you let one of these edges go to 0, say the middle one goes to 0, then you are in this line on the side, and then you sort of let the new edge come out, and then you end up being in this simplex up here, or alternatively, you now let the simplex grow sort of in the opposite direction, and then suddenly you're in a different cell over here, where you end up having a different Teichmüller marking. Namely, here you had the one that sends this loop and this loop to the generators of the free group, and here you have that this loop is sent to the one generator, the other loop is here being sent to the opposite, so the inverse generator, the inverse of the generator in the free group. And so on, and you get like a really big space out of all these simplices, and all the smaller simplices show up as well. And I mean, well, the complexity of this picture already illustrates that this is a huge space. Okay, I will stop this video now, and in the next video, we'll talk about the main result. Welcome back to the main result of this project. So let's go through it. So suppose we have an algebraically closed field. I mean, in principle, you can avoid having that, but we'll do it for simplicity. And the G is a number greater or equal to 2. Then our result is that we have constructed such a non-Archimedean analog of Teichmüller space. And this thing is a smooth, separated, K-analytic Dilley-Mumford stack. So K-analytic means Berkovich analytic Dilley-Mumford stack. And it doesn't have a boundary. I want to point out that it's not quite proper, but it's close enough to being proper, since it is not quasi-compact. So, I mean, the only thing that fails for it to be proper is the quasi-compactness. Okay. And the next step of this result, so first we have constructed and we have shown it is a reasonable Berkovich analytic space / stack. And the next part is that one can look at the natural tropicalization map that goes from here to there. What is it? Here it's just an x, phi. The map sends it to the class of the skeleton together with a vertex weight that just keeps track of the reductions of each point. Or the genus of the normalization of each reduction, rather. And it sends this marking to the tropicalization of the marking, which is really easy to define, simply because, well, the fundamental group of the skeleton is in fact isomorphic to the fundamental group, so even naturally isomorphic via a retraction map to the fundamental group of the Berkovich analytic space, and then you just compose it with the phi that is given to you, and that is your tropicalization of the Teichmüller marking. And now this natural tropicalization map has a continuous section that makes the tropical Teichmüller space into a strong deformation retract of the non-Archimedean analytic Teichmüller space. Okay. this is the main result. I want to quickly illustrate a little bit more what the tropicalization map really does. So just to be on the safe side. So we take X, a stable model of X, which exists since we assumed that K was algebraically closed. If it wasn't algebraically closed, then you have to sort of go to a finite extension thereof, but let's not cloud our notation too much. So, so X over K is the generic fiber, then the stable model, say, could look like this in the special fiber. And now we define the skeleton. It's really the same thing as the metric dual graph. So first of all, what's the dual graph of the special fiber? Well, we take a vertex for each of the components and connect them for every node that connects them. So we have two vertices. We have a self-connection here, we have a self-connection here, and you have one edge that corresponds to the connection over there. And now what happens, what is the genus function that I only sort of skipped over up here, this H, this vertex weight, what is it? It is the genus of these normalized components. So it's 0 everywhere, but at the two vertices, and at each of the vertices, you just normalize the corresponding component, and that then take its genus. So in this case, that's 0 and 0. So we don't even draw it, and then we're good. This is what H is. And well, in more complicated situations, of course, you have to do more work, but here we are okay. And the term metric dual graph means the following. I mean, first means it's induced metric from the Berkovich analytic space, but more down to earth, it's if you look locally around a node, then this node is given as by x times y equals r, where r is an element in the valuation ring of K. And then you use this r to define the edge length of the corresponding edge. So the length of the corresponding edge is just the valuation of r. So of this edge, this is the valuation of r. And similarly for this node and this edge and this node and this edge. Okay, so that just explains further what this tropicalization map is, and sort of gives a bit more sense of what goes into this theorem and what the situation this theorem is describing is. And a nice corollary of this theorem is the following. It's true that we have this non-Archimedean analytic stack built in, and then we have a locus of Mumford curves in this stack. That thing is not a stack, it's actually a nice, reasonably nice Berkovich analytic space. Just there's no stackiness involved if we have Mumford curves in this case. And the corollary is now, if we look at this locus of Mumford curves in this tropical model, in this analytic moduli space, then Kala-Wogman outer space is a strong deformation retract of this locus of Mumford curves. That's like a neat little corollary here, and yes, it should be an AN, otherwise it's not true. And that just a neat little corollary that needs recording. Okay, so this is the main result. So it has two things. First, non-Archimedean Teichmüller space exists as a non-Archimedean analytic dealing Mumford stack with reasonably good properties. And well, the tropicalization map identifies the skeleton of this non-Archimedean analytic Mumford stack with the tropical Teichmüller space. In the next video, I will talk about the strategy of how to construct this thing, and then it will also become clear why sort of the second part of this theorem follows rather straightforwardly. In this final video, let us now discuss how to actually construct this non-Archimedean analog of Teichmüller space that the theorem was about. So the first step is to construct the tropical Teichmüller space in this language of poststacks that we talked about earlier. And actually we used the language of cone stacks, but yeah, could have also used the poststack language. And the crucial point here is the following question, namely, we know what the fundamental group of a metric graph is, but what is the fundamental group of the metric graph with the vertex weights of the tropical curve? And that's an open question, and there are different answers to this. And depending on the situation, you want to choose a different definition. Just to illustrate the problem a little bit, well, you have your, say, your metric graph. It deforms to something like this. And now the big question is, if we have a marking of this metric graph, what does the marking deform to? It seems like there's sort of a collapse in marking going on, and that's exactly the tricky thing I tried to point at earlier as well. And I mean, there's really something going on that one has to take care of. And the thing, the way to take care of it is to not look at this deformation, but rather to look at a different deformation of the tropical curve, namely, and not to a such a tropical curve like this, but rather to a metric graph of groups. So what's a graph of groups? That's a notion that has been introduced by Serre and further studied by Bass. And it really is just a graph with decorations by groups at vertices and edges and connections between them. And we do something very simple. We just replace, we just decorated the new object with a free group with one generators at this particular vertex. And of course, if we are contracting several loops, then we have to use free group with several generators. But anyway, in this simple case, this is that one. So we look at a deformation here, and it sort of, we let our tropical curve or this metric graph deform to this metric graph of groups. Well, Bass and Serre do not talk about metric graphs of groups, but it's easy generalization thereof. And then we use this part to and I mean, then sort of the Teichmüller marking that we had, namely the outer isomorphism clause between this thing and the free group, that just deforms nicely in this language. And only then, once we have this nice deformation going, we again forget parts of the deformation. And if we do so, then we end up getting a reasonably nice family for everything to fit together. And the main point is, if we do graphs of groups, then the fundamental group of this new thing, I mean the graph of groups, let's just call it GG of gamma. I mean, it's a horrible notation, but anyway, is still F2 in this case. Or rather in general, FG, where G is the genus of the metric, the weighted graph. And if we do so, and if we consequently apply these techniques of graphs of groups, we manage to actually construct a tropical modular space and the language of cone stacks, which is kind of like stacks over posets. Okay, before we continue, a quick remark on at this point. The crucial answer here is that, I mean, what is this fundamental group? Well, it is the fundamental group of this metric graph of groups. There are other situations in tropical geometry where your answer will be different. I just want to warn you about that. And so that's an important thing to know, that there are other answers to this question. But ask me what other answers I can propose. I mean, I know of at least 2 answers. Okay, the next step is now to lift the tropical Teichmüller space to an algebraic stack, and that sounds completely crazy, but it's not that bad actually. So what do? The keyword is use the theory of Artin fans, and well, what you do is you take the post-stack diagram that we have seen above for M2 and associate to each of these stable vertex-weighted graphs. A cone in the category of stacks. And what is that? That is an affine space generated by the number of edges of the graph. And you mod out by torus also to the power of edges of the graph. So this is our incarnation of a rational polyhedra. I mean, it is our incarnation of r greater equal to 0 to the power e, which sort of parameterizes all of the edge lengths in the category of algebraic and in fact logarithmic algebraic stacks. And I mean, you have this. Then you have the maps that are induced between the graphs whenever there is a contraction that induces nice logarithmic maps between these things. In fact, they will be strict, et al, and whatnot. And then at the end, we have a big diagram in the category of stacks, and you take the 2 co-limit. The 2 co-limit means that you take a limit in the category of stacks. And that just remembers the right automorphisms, so to say. Okay, and now, finally, we'll take a fiber product. How does that work? We think about mg log, the modular space of logarithmic curves, and look at the tropicalization map that we described above and beef it up a little bit and describe it and get sort of our lift of the tropical modular space. Above it, you have the lift of this tropical Teichmüller space. And we quite literally take the fiber product now of these 2 things and get a new space that we, for simplicity, call TG log, which I hesitate to call logarithmic Teichmüller space because that invokes too many association, which is not true, but let's just call it TG log. And I want to point out that with this construction as a fiber product, I mean, we really do having a logarithmic curve together with that is sort of that, and then you take its tropicalization and you take here the extra data of a Teichmüller marking on the tropicalization. So really on the resulting thing. So that is exactly the intuition that I wrote in the earlier parts. And also, since this this A upper star, this lifts these cone stacks or post stacks, then this actually is in the same category. So it makes quite literally sense to talk about fiber products. And you could use similar techniques and slight modifications, but in principle the same techniques to also construct the Mumford uniformization of a non-Archimedean curve this way. And then the above thing, when I put these quotation marks, that would just fall away. Anyway, from here, we can deduce that this space here is, first of all, log smooth, in fact, smooth itself. That's also fine. And a DM stack. It is locally of finite type, but not quasi-compact. It's really only locally of finite type. So I mean, that's the source of why the space later will not be proper over the integers even, and it is universally closed. That's also great. So you have limits. The one thing it is not separated. But the statement of the theorem says that the space we want in the end has to be separated, so one has to work a little bit further. And for this, we apply Renault's generic fiber functor. So we want to define this TGAN, and this will be a subspace of a compactified version thereof. And this thing is what we really define here. So what do? First things first, we take this TG log and we construct it with these tropical methods and then lifting. Then we look not at then we forget the log structure. Then we take, I mean, this thing will now be just a stack defined of the integers. We now take the base change to the evaluation ring. We complete it. And I mean, we then complete it at the special fiber. That's always possible. And then we apply Renault's generic fiber functor. And that thing ends up now being exactly the space we want. And sort of the funny thing is we have something very non-separated here, but the generic fiber functor just makes things that don't look separate at all, as long as they're only not separated in a particular special fiber kind of way, into something separated. And that's sort of the magic of Renault's generic fiber functor, that suddenly the space we're constructing is also separated. Okay, that ends the story, and I will stop now.